Correct me if I'm wrong, but we discussed the concept of sampling error. So sampling error. And I told you, whenever we take samples, and these samples then are used to make a prediction about a population, we always have this sampling error in it. So a sampling error is inherent. You can't avoid it. Whenever we take samples, there will be a sampling error. So one of the illustrations is, for example, I want to know what is the average height of all students in the university. So what is the population mean of height of students? In uni. And that would be, for example, very important if, for example, I wanted to produce and manufacture a University of Kent onesie, which you can buy, by the way. Yeah, there is one. But if I get it wrong, then and make all the onesies too big, I would waste material, and you might look like you need a GPS in it because it's so big. If I make it too small, well, then you will go like that. So not good either. So I need to find out what is the average height. And I take samples. So for example, I use 3 students, measure 3 students, 175 centimeter, 178, 181 centimeters, let's say. Yeah? So that's my first sample with 3 observations in it. And I say, okay, good. I want to take another sample, let's say 164, 170, and 176 centimeters. That's my second sample. Sample 2. And that was sample 1. And these are obviously students from this university. So I now can calculate the mean of both. Can you quickly calculate the mean of those? $170, 178, and this here is 170, exactly 170 centimeters. I tried to make it easy for myself, so you can do that in your head. And what we see is that these sample means are different from each other. But they still represent the same population. They are taken from the students. Which basically means there is an inherent error in it. There's nothing I can do about it. In one case, I get 178 centimeters, and the other one, I get 170 centimeters. Both are correct, per se, but they're different. But then, this carries the question, how different is different? Are they statistically significantly different, or are they just simply due to sampling error? And we discussed then the concept of the null hypothesis, which is abbreviated like that, H0. And this null hypothesis says there is no difference between the sample means, other than caused by the sampling error. That is the null hypothesis. And mathematically, we can express that as x bar 1, sample of 1, or the mean of one sample equals the mean of the second sample. And of course, we would say 170 centimeters is not 178 centimeters. But the way we write it here means they are the same apart from the sampling error. And we can also formulate our alternative hypothesis, H1. And we say there is a difference between the sample means. There is a difference between sample means. And this difference is caused by the sampling error. We can't get rid of it. By the sampling error and additional factors. And in this case, we would write x bar 1 is unequal x bar 2. Right. So far, so good. But how do we find out which of these two hypotheses is true? So the question is how to find out if we believe H0 or H1. We can have only one of them because one is the opposite of the other one. Either there is a difference or there isn't. How do we find out? Well, luckily, there's a process, it's a fairly complicated process, which is called the ttest. And it doesn't have anything to do with a cup of tea. We know that the University of Kent has a tea society. Have you heard about that? Is anyone member of the tea society? No? Last year we had one guy who was member of the tea society, and I asked what they are doing, and he said, they are testing tea, so it's ttest. Not quite, this is a different one. This is also known as student ttest. And allegedly, or I have no reason to doubt this information, it was developed by a very clever guy who used to work for the Guinness brewery. And his job was actually to check. He was involved in quality assurance. So the ideal job for a student, you just take several samples of Guinness and you compare the outcomes and you compare your studies. And he developed this test, but his employer didn't want to know where this test has been developed and how the Guinness brewery is using this test, so he couldn't publish it under his rightful name, and so he published it under the pseudonym Student, and ever since it's known as the student t-test. Now what the student t-test actually does, it compares, this t-test compares the means of two samples and then gives us a probability can't spell, that these two samples come from the same population, that these two samples are similar apart from the sampling order, that samples only differ because of the sampling error. We don't want to go too much into probability because you have an intuition about probability. If I say to you, there is a 50% probability that it's going to rain tomorrow, you know what this means. It might rain or not. Right? Now, how does this t-test work? I'm not going to tell you actually how this works. I just want to give you the, sort of the outcome. Now, let's say we have our two samples that I had earlier. What was it? 175, 178, 181. And I want to compare that to these three observations. So I would do what is called this t-test on that. It's a very special t-test, and I will go back to that in a minute. There are different t-tests. But if I tested these two samples, I might find that they are similar or not. What do you think? Just simply from your intuition. Are these two samples, the two sample means, are they different or are they the same? What do you reckon? Are they different or are they the same? Do they come from the same population, or, is this just simply because I picked out all the basketball players? They are the same? Yeah? How sure are you?
You said the same population, you said all the students here. So.
Yes. Are they the same, or is there something fishy going on?
They're on the lower end of those ones, so maybe you did just pick like the left hand.
Okay. So, are they the same or yes? Yeah? How sure are you? How sure are you? Are you 90% sure? Where shall we put a sort of a line? When are they no longer the same? Where would you say? Let's do the following. Here's my sample. 177, 178, 179. That's my first sample. And my second sample is 176, 178, 179. It's my second sample. Are they the same? Yeah? Would say yes? Okay. So pretty sure. How many of you think that they are the same? Hands up. How many of you think they are not the same? I can't see a single hand. So we are pretty sure. So we are almost 100% sure. Yeah? Okay, now I compare this one with 170, 100 and, so that's 170, 174, 175. What about these two? Sure? Less sure? Could be. Might not be. Yeah? So less sure. So could be that, say, 50% of you say. Yeah? Let's say 50%. Where do we draw the line? Actually, a very common line is only 5% sure, or 5% confident. This is also called the confidence level. But this is a very common thing. Yeah, that's all right. And that is 0.05. Yeah, 5%. So in other words, if we do the t-test, if we did a t-test, and this t-test gave us a probability, or it's also called a p-value. This p-value is the same as a probability. And it gives us a p-value of, say, 50%, then this would be similar to the comparison between these two here. Yeah? We are 50% sure that they are all right. So this means, well, probably okay, these two samples. Now the p-value, a p-value can range between 1, which translates to 100%. We are 100% sure that they are the same, to 0. We are 0% sure that they are the same. Well, if we are 0% sure that they are the same, it means we are pretty convinced that they are not the same. Yeah? That makes sense? So this is where the p-value can be between 1 and 0, or 0 and 1. From 0, not at all the same, to 100% the same. And the rule is, I want to write that down, if the p-value that we get from the t-test, if the p-value is lower, is smaller than our confidence level, then the two sample means are different. Or in other words, we said our null hypothesis, the sample means are the same, it's wrong. Our null hypothesis is the two sample means are the same, but if p is smaller than this alpha, we reject the null hypothesis. We say, sorry, it's not true. And there's a very simple sort of mnemonic. Do we have any Australians here? Anyone from Australia? No? Then nobody can criticize me for my accent. If P is low, H naught must go. If P is low, H naught must go. So H naught is not applicable. Samples are different. If P is high, H naught can stay. Yeah? So, if P is low, we reject the null hypothesis. the samples are not the same. If P is high, H naught const I. You probably won't forget that in a hurry. You see? H naught can stay, and therefore samples are the same. So, for example, I give you a p-value. P-value is 0.7. And I want my confidence level, my alpha is 5%, so that's 0.05. Yeah? And my assumption was H naught. The two sample means are the same. What do I do with that? Now, P is higher than alpha. So, if P is high, H naught can stay. So I accept the null hypothesis. Yeah? Accept the null hypothesis. And I say, yes, I'm fairly certain that the two means that the two samples are the same. They are from the same population. Okay, I have a p-value is 0.0001. My alpha is 0.05. This is a very common alpha. What do I do with that? I reject the null hypothesis. So, reject null hypothesis, and in a way, accept the alternative hypothesis. Yeah? Which means the two means are not the same. Are you happy with that? It's pretty straightforward. But how do we do this t-test? Well, first of all, the bad news is that there isn't just simply one t-test. There are combinations of t-test. The first one, and the most common one usually, is what I just showed you. We have two samples. So, two samples. And these samples are taken independently. They are independent, taken from each other. So I take 3 students over here, measure them, and I take 3 students over here. These students have nothing, there's no connection between these 3 students, between these samples. Though they are independent samples. I can also do a different test. 2 samples. But I use the same students. That is very useful if you, for example, do drugs. No, let me qualify that. If you want to test something, an effect. So, for example, I take 3 students and measure their blood pressure. And then I do something with them. I hug them. Yeah? And then I measure their blood pressure afterwards. Huh? Would be good? Yeah, I know, yeah. Yeah? This is, the samples are not independent. Here the samples depend on each other. So the samples are also, if you like, they are paired.
What, because they've been treated the same?
They are from the same student. Yeah? From the same student.
So using the same lot again?
I use the same lot again. Yeah? That is the dependent or paired t-test. Now, it could very well be, if we go back to this one here, that the samples that I'm looking at have the same or different variances. And we discussed what a variance is, where we just simply take the difference between the individuals and the mean, square that, add them all up, and divide by n minus 1. Yeah? It could be that they have the same or different variances, and in both cases, the calculation would be different. Whew. And we have an additional complication. We can ask, what is our alternative hypothesis? The null hypothesis is, in both cases, is always the sample means are the same. We can have, however, a situation where we say our alternative hypothesis is not the same. This means that one of the samples is bigger than the other. Sample means is bigger than the other. But we haven't defined which one. It could be that x1 is bigger than x2, or it could be that x1 is smaller than x2 bar. Yeah? So we have two options for that. That is, because we have two options, this thing is called a two-tailed test. However, if we say our h1 is x1 is smaller than x2, and we say that, we explicitly state that, this would be a one-tailed test, where we explicitly state that specifically one is smaller or bigger than the other one. Okay? Are you happy with that? And we get different combinations of these things. Now, how do we get this information? How do we get this blooming p-value? Luckily, well, in previous years, people had to use sort of tables. And it's a mess. Luckily, most software, spreadsheet software, does it for you. In Excel, in Number, and in Google Spreadsheets, you can do a t-test. And the function for that is ttest. You put in your first data set, dataset 1, comma, dataset 2, comma. It assumes an alpha of 5%. Then you have to tell the program which test it should use. You put in a 2. This indicates that is a two-tailed test. You just assume that the two sample means are not the same. If you want to be more specific and say sample 1 is bigger than the sample 2, then you go for a one-tailed, and this would be a 1. And lastly, you need to tell the program what kind of test you want. Is it a paired test? Is it a before and after? Before I hug you, and then after I hug you? Or is it completely independent samples? And if it is independent, do they have the same variance? And usually my advice would be, if it is not a before and after, if it is an independent test, go for option 3 that you put in here, because that is unequal variance. And usually you don't have the same variance anyway. So, if you wanted to calculate a p-value, dataset 1, dataset 2, 2, 3. That would be the relevant stuff for you. Okay? Now, let's see how this looks like.